Made a video previously about the Coulomb force between charges, and I want to build off of that idea to unpack the idea of an electric field. So let's say that we have some charge in the middle of the whiteboard here, and we're going to call that charge plus Q. Now, per what we saw with Coulomb forces, if I had another charge, and so by convention, I'm going to call this charge plus Q naught. This is a test charge. Essentially, what we're going to do is we're going to test what Coulomb force would be experienced if we put it at some distance r away from the plus Q, the original charge that we started with. And so by way of the Coulomb force between charges, we could say that the Coulomb force, I'll call it Fc, is equal to K, that's the Coulomb constant, and then, and I'll keep with the color coding here, multiplied by plus Q, multiplied by the test charge, Q naught, and then divided by the square of the distance between those two charges. That's the Coulomb force. And as we talked about, while this mathematically has a similar structure to the gravitational force between two masses, in the case of charges, we also have to take into account the relative signs of the charge to each other, because if both charges have the same sign, i.e., they're either both positive or they're both negative, then the charges are going to repel each other. However, if the charges have opposite signs, so if one has positive and the other has negative, or the other has positive and the other has negative, then you're going to have an attractive force. So in this particular situation, the Coulomb force that the test charge would feel would actually repel it further away from the original plus Q charge at the center of the whiteboard. So we would have a Coulomb force that would go in the direction of the orange arrow that I just drew. Now, let's hypothetically say that instead we put our plus Q naught test charge right here. In this particular case, the Coulomb force would go up like this. If I put my test charge, say, right here, the Coulomb force would go in this direction. If I put my test charge, say, over here, now the Coulomb force is going to go off to the left. You can probably see a pattern here. You have arrows that are spherically emanating from this red plus Q charge in the middle. And that's because if you were to bring in a second test charge, this is what the directions of those forces would be at those different locations. And so I can just extend these lines. So if I was to draw like lines through the orange hypothetical Coulomb force lines for different hypothetical positions of our test charge, by extension, it would also look like this, and like this, and like this. And I'll also put some little arrows in here to suggest that at these different locations, that's the direction the Coulomb force would be. So what I have just drawn in here is I've just drawn in an electric field. And that electric field is due to the original plus Q charge in the middle. Okay, I'll actually put the electric field due to plus Q. And so this is not a completely new concept. This is an extension of the Coulomb force concept. It's just that the red that you see now, it's the same color as that one charge Q because it's only because of the presence of that one charge Q. You can think of an electric field before you ever bring another charge into the situation. So you can think of the electric field as this hypothetical map where if another charge was introduced to the situation and it was placed at some location in that electric field, we should be able to ascertain what the Coulomb force experience would be due to the presence of the original charge in which we drew the electric field to begin with. And so this electric field is defined as K plus Q, because remember, it's a hypothetical map for the existence of that first charge, divided by R squared. It looks almost like the Coulomb force you see in the upper left-hand corner, but you see how it's missing the test charge because the test charge hasn't come into the game yet. So quite simply, the electric field is this hypothetical map of what possible Coulomb forces would be once you do bring, say, a test charge into the game, where you would have to consider, okay, well, where did I put it? And by where I put it, I mean, how far away was it? And so it's pretty straightforward, actually, if you have an electric field to calculate what the Coulomb force would be if you take a second charge and you put it in the presence of that electric field. And quite simply, the Coulomb force, when you want to write it in terms of the electric field, is going to be equal to whatever the second charge is going to be that we bring into the situation. So let's say we bring a test charge in, and then whatever the electric field is at that particular position that we put the charge. Now, you probably don't have to think too hard to see a very similar structure on the left and right here. If the electric field is K plus Q over R squared, and the Coulomb force is the electric field times plus Q, then you should have the same structures you have on the far left, i.e. the Coulomb force is K plus Q naught divided by R squared. So once again, this electric field idea is not a new concept. It's an extension of the concept of the Coulomb force that you have already been practicing. But now it allows us, before any other charges get into a situation, it allows us to map for the presence of a single charge what possible Coulomb forces could be experienced when other charges are placed at different locations from that original charge.